Good day, everyone. My name is Charles Lloyd Tempelayes, and I will present the ultimate module for this school year's DMAT certs. This lesson will cover the fundamental theorem of calculus, solving definite integrals, volume of solids, and the mean value theorem for integration. Let us begin our first lesson, which is fundamental theorem of calculus. This theorem is an important thing to know. The first theorem is that the derivative of a function's antiderivative is the function itself. So this might be a complicated looking equation, but in reality, it's just implying that the derivative of a function's antiderivative is itself. The second equation, or the second theorem rather, talks more about areas under a curve. So the integral of a function given two limits is equal to the difference between the values of the integral given the limits. We will discuss more of it in definite integrals. Now here is definite integration. Definite integration is the term for the process wherein you find the area under the curve bounded by two limits in the Cartesian plane. So let's assume that we have a curve graph on the Cartesian plane. So it goes like this. Here's our Cartesian plane. Here is our curve. Now we want to know the area wherein we put two limits here or two values of x. Let's say x equals a and x equals b. We want to know the area under this curve. How do we find it? We will use definite integration. This is derived from the concept of Riemann sums, which is the summation of infinite rectangles formed by the lines that are inside the curve. Definite integration is the most efficient way to simplify that summation. The area under the curve can be either positive, negative, or zero. So area can be either positive, negative, or zero. Also, it is not necessary that B is greater than A. This is for this reason, that the area can be negative. Sometimes, if a curve is graph opening upwards at a certain interval or at a certain limit, like this, the area is negative. Meanwhile, if the curve is graphed downwards, the area is positive. So how does the area become zero? The area becomes zero when the curve goes both ways on the given bounds. So we have a part which is positive and we have a part which is negative. If these two are equal, then the area under the curve becomes zero. Now, we will solve problems regarding definite integrals. Here's our first example. Evaluate the definite integral of quantity x squared plus 5x plus 6 dx from x equals 1 to x equals 6. So we can see, we can just simply integrate the given integrand, just like what we do in indefinite integration. So we have x squared is x cubed over 3. Since we just add 1 to the exponent, then the resulting exponent is divided on the given term that we integrated. X cubed over 3 plus 5x squared over 2 plus 6x over 1, which is just 6x, then plus c. However, in solving definite integrals, for it to be easier, you should not put the plus c, since when we subtract the integral from the upper bound to the lower bound, the c will cancel out. So it makes more sense to not put the arbitrary constant, since it is basically useless in definite integration. Instead, at the end, we will place a vertical line long enough to cover the equation. Then put the upper bound and lower bound the same way as this one in the given. So the lower bound is here and the upper bound is there. We will do the same thing. This is the upper bound, this is the lower bound. This means that we will perform subtraction when x is at the upper bound, which is 6, subtracted by the value of the function on the left when x equals 1. So let's find out the value of this definite integral. 6 cubed over 3 plus 5 multiplied by 6 squared over 2 plus 6 times 6 minus quantity 1 cubed over 3 plus 5 multiplied by 1 squared over 2 plus 6 times 1. 6 cubed over 3 is 72. 216 divided by 3 is 72. 5 multiplied by 6 squared is 180 over 2 is 90. 6 times 6 is 36. Then we have 1 cube over 3, 1/3. 5 times 1 squared, 5 times 1. So 5 over 2 plus 6. This gives us 72 plus 90 plus 36. 126 plus 72, 198. Minus, we add this. So the least common denominator is 6. 6 divided by 3 is 2. Plus 5 times 3, 15. 6 times 6, 36. So this is 198 minus 53 over 6. Then, subtracting, we get 198 times 6 is 1188 minus 53, which is 1135 over 6. So this is the answer for our first problem. Now for the second problem. So we have this integral. We have x to the fourth power over 4 minus 37x squared over 2 plus 84x. When we integrate this, y, x cubed plus 1, 4 divided by 4 minus 37x squared over 2, then plus 84x from 3 to 4. So we just simply substitute. So we have 4 to the fourth power over 4 minus 37 multiplied by 4 squared over 2 plus 84 times 4 minus 3 raised to the fourth power over 4 minus 37 multiplied by 3 squared over 2 plus 84 times 3, enclosed in parentheses. 4 to the fourth power over 4 is 64 minus 37 times 4 squared is 37 times 16, right? 37 times 16 divided by 2 is 296. 84 times 4 is 336 minus 81 over 4 minus 37 times 3 squared, which is 9, 333 over 2 plus 84 times 3, which is 252. 64 minus 296 plus 336 is simply 104 minus 81. So the LCD is 4. 81 minus 666 plus 1008. This gives us 104 minus 342 plus 81, which is 423 over 4. This gives us 416 minus 423 over 4, which is negative 7 over 4. So the final answer for this problem is negative 7 over 4. As we can see, the area is negative, which means that we will easily determine that this function might be a function wherein the area above the curve is greater than the area under the curve. So we subtract those two and get a negative answer. Now for the next problem, what if we need to perform a U substitution. How will we be able to solve such a problem like this one? We will do the normal U substitution for this problem. So this problem asks us to evaluate the definite integral of quantity 12x multiplied by quantity 2x squared minus 1 in closing parentheses squared with respect to x from x equals 4 to x equals 5. So by U substitution, we get U equals 2x squared minus 1. Then getting the derivative is du equals 4x dx. Just like normal indefinite integration, we will do the same thing. Do we have a 4x dx here? Yes. So this clearly works. So we can factor out the 4x from 12x to have 3 multiplied by 2x squared minus 1, 4x dx. And this will be our du. And this will be our u. Remember, we will substitute x with u, which means that our lower and upper bounds should be changed. These two must be changed. Or should I say, must be adjusted. For use constraints. So we will substitute x to u. So we have x equals 4, which gives us u equals 2 times 4 squared minus 1 equals 31. Then x equals 5. We have u equals 2 times 5 squared minus 1 equals 49. So from x equals 5 and x equals 4, it becomes u equals 49 and u equals 31 respectively. Then we substitute all of that to our new definite integral. 31 at the bottom, 49 at the top, and we have 3u squared du. So as we can see, the important thing here is that we need to change x to u just like how we change it with the u substitution. You should take note of that because this is a careless thing that you might do when using definite integration via u substitution. Now knowing that, we integrate u with 3u squared with respect to u, which is simply 3u cubed over 3 from 49 to 31, which is simply u cubed from 49 to 31. So we have 49 cubed minus 31 cubed. And simplifying that, we get 87,858 as our final answer. Pretty big number, but at least the area is positive. Now, let's try these exercises. So we have these three algebraic problems. But what if instead of algebraic problems, you encountered trigonometric problems? This will be our next case, wherein a definite integral has transcendental functions. And the first one that we will discuss is trigonometry without u substitution. So evaluate the integral. We evaluate the integral of this one, secant x tangent x dx from 0 to pi over 4. As we can see, this is simply the derivative of secant x, right? As you can recall from differential calculus, this is just the derivative of secant x. With this in mind, we can easily integrate this function. So the integral of this one is simply secant x from 0 to pi over 4. And getting the definite integral, we have secant pi over 4 minus secant 0. Secant 0 is just 1 over cosine 0, which is 1. So we have 1 here. Then, for secant pi over 4, this is just secant 45 degrees. So 1 over cosine 45 degrees, which is square root of 2. 1 over square root of 2 over 2 minus 1. Then this will be flipped. We get 2 over square root of 2 minus 1. Then we cancel this one so that square root of 2 remains. And this is our final answer. Square root of 2 minus 1. Pretty easy, right? What if we incorporate u substitution in this problem? Like this one. So from 0 to pi, we evaluate the definite integral of cosine quantity x over 3 with respect to x. So as we can see, we can easily do the u substitution. U equals x over 3. And du equals dx over 3. Or 3 du equals dx. With this, we will adjust the lower and upper limits. So if x equals 0, then u is 0 over 3, which is 0. Then if x equals pi, then u equals pi over 3. So the new integral will be the integral of cosine u. Since dx is 3 du, we multiply 3 du here. And then the upper and lower bound, 0 and pi over 3. Cosinus integral is simple. This is just sine u, which means that the whole integrand can be integrated into 3 sine u from 0 to pi over 3. At u equals pi over 3, we have 3 sine pi over 3. Then at u equals 0, we have 3 sine 0. Pi over 3 is 60 degrees, so we have 3 multiplied by square root of 3 over 2 minus 3 times 0. So this is 0. We have 3 square root of 3 over 2 as our integral. And this is for trigonometric functions. But what if it's exponential functions instead? The next problem will give you the exact situation. Now, as we can see, we evaluate the definite integral of quantity 4x minus 7 multiplied by 2 raised to quantity 2x squared minus 7x plus 3 from x equals 1 to x equals 2. So, as we can see, we need to use u substitution here. U equals 2x squared minus 7x plus 3. Getting the derivative, we have 2 times 2, 4. 2 minus 1, 1. So 4x minus 1 minus 1, 0 times 1, 7 dx. And this is the exact form as the one in the given problem. So this whole thing is just u, du. And this exponent is just u. Now we have the integral of two raised to u du from x equals 1 to x equals 2. But remember, we will adjust this one with respect to u. So u equals 2 times 2 squared minus 7 times 2 plus 3 for the upper bound, which is 8 minus 14 plus 3 equals negative 3. And for x equals 1, u equals 2 times 1 squared minus 7 times 1 plus 3, which is equal to 2 minus 7 plus 3, negative 2. Negative 2, negative 3. Just like what we said earlier, if b is less than or greater than a, it doesn't matter. Now integrating, we have 2u over ln 2 by using the exponential integration rules from negative 2 to negative 3, which is 2 raised to negative 3 over ln 2 minus 2 raised to negative 2 over ln 2. This is 1 over 8 times 1 over ln 2 minus 1/4 times 1 over ln 2, which is 1/8 minus 1/4, negative 1/4 ln 2. We put it in the denominator as well, since both of them are denominator and its multiplication. So the final answer for this problem is negative 1 over 4 ln 2. Or you can insert the 4 so that it becomes negative 1 over ln 16, 2 raised to the 4th power. Any will do, but I prefer this one since it expresses the natural logarithm in terms of prime numbers, and it's easier to compute on a calculator. Now, these are the lessons for definite integration. Hello, everyone. So this is the continuation for the Module 8 of the Calculus lesson in Department of Mathematics, Inserts. So for our third and final lesson, we will discuss mean value theorem in integration. In the derivative part, we already discussed it on the third term. However, it has its integration counterpart. Instead of the derivative being obtained, we have the integral being obtained in this case. So as we can see, we have here f of c, which is the original function, then f of b or f of a, the capital F refer to the antiderivative or the integral of f of x. So we still have the same form, but this time it's the function that has the c in it. Remember that the mean value theorem for derivatives has f prime of c equals f of b minus f of a over b quantity b minus a, right? It's the same because here we have the derivative and here we have the original function. And the derivative of a function's integral is the function itself from the first fundamental theorem of calculus, which we discussed earlier. So how do we use mean value theorem in problems? So here is an example. Find the point C that satisfies the mean value theorem for integrals on the interval 1, 4. So we need to find the point C that satisfies this theorem, right? This means that we have to find the mean for this function. I mean the value of x wherein you can see the mean. So we have f of x equals 3x squared minus 2x. And just like what I have said earlier, we have f of c equals f of b, capital F of b minus capital F of a over quantity b minus a. So we have b equals the upper limit, right? Which is 4. And then a is the lower limit, which is 1. So we have f of c equals capital F of 4 minus capital F of 1 all over 4 quantity 4 minus 1. So first we need to find the integral or the antiderivative, which is the integral of 3x squared minus 2x dx. So if we integrate this, we have three x cubed over 3 minus 2x squared over 2, which is equal to 3 divided by 3 is 1, which is x cubed minus x squared. This means that we need to get the value of x cubed minus x squared at x equals 4 and x equals 1. So we have, let's put an equal sign. Four cubed minus 4 squared minus quantity 1 cubed minus 1 squared all over 4 minus 1. This is 0. This whole thing is 0. This is 64 minus 16, which is 48. Then 4 minus 1 is 3. So we have 48 minus 0 over 3 equals 16. So the value, so f of c must be equal to 16. Now we have to solve for x, or the value of c. F of c is equal to 3c squared let's just erase this. F of c equals 16. This means that 3c squared minus 2c equals 16. Or 3c squared minus 2c minus 16 minus 16 equals 0. By factoring, we get that this is 3c minus 8 multiplied by c plus 1 equals 0. So this means that c equals negative 1 or 8 over 3. However, as we can see, the interval is at 1, 4. This means that we discard x equals negative 1 since it is not in the interval. This implies that the only value of c is c equals 8 over 3, which is indeed between the interval 1 to 4. So the correct answer for this problem is at c equals 8 over 3. We will try another problem regarding mean value theorem for integrals. So this time, we have the interval 3, 7, and f of x equals x cubed. So first, we have f of c equals quantity capital F of b minus capital F of a all over b minus a. At this problem, we have a equals 3, the lower limit, and 7 as the upper limit, which is b. So we have quantity f of 7 minus f of 3 all over 7 minus 3, which is 4. So all we need to find is f of 7 and f of 3. Now, we will integrate f of x. So we have x cubed, whose integral is simply x to the 4th power over 4. Since all you have to do is to add the exponent by 1, and the resulting exponent will be divided to the resulting algebraic expression. So x to the 4th over 4. Now we have f of 7, capital F of 7, which is 7 to the 4th power all over 4 minus 3 to the fourth power all over 4. All that over 4. So that is f of c. And f of c, we just substitute c to f of x. So we have c cubed equals this. Remember, f of c equals c cubed. So from here, it becomes this one. 7 raised to the fourth power is 2,401 over 4. Minus 81 over 4. All over 4. This gives us 23,020 all over 4 over 4. Canceling, we get 2,320, which is 580. Then canceling one more time with the 4 below, we get 580 over 4, which is 145. So c cubed equals 145. And solving for c gives us c equals cube root of 145. The other two roots of c cubed equals 145 are not real. They give imaginary roots. But in mean value theorem, we talk about real numbers. So the only valid solution is c equals the cube root of 145. This is approximately equal to 5.2536. Is it between 3 and 7? Yes, which means that this solution works. So the correct answer for this problem is c equals cube root of 145. In this mean value theorem, we can apply this concept into word problems. Here's a word problem on mean value theorem. A factory creates cubicle boxes with a random edge length selected between the interval 4 to 8 inches. What is the average surface area of the cube that can be made inside this factory? As we can see, we have the formula for surface area, which is 6s squared, where s is the side length of the cube. So this will be our f of s. Instead of x, we will solve the problem with respect to s. So this is our small f of s. Getting the integral of this function, the capital F of s, we have 6s cubed over 3. This is the antiderivative, which is equivalent to 2s cubed. Now, we can apply the mean value theorem. Remember that our b is 8, then a is 4. We have f of c equals capital F of b minus capital F of a all over b minus a. So f of c is 6s cubed, but since the variable inside is c, it becomes 6c squared. I mean 6s squared, then by substituting c, we get 6c squared, not cube. The cube one is here, the big F. we have 2 s cubed. S equals 8 for big F of B. So we have 2 multiplied by 8 cubed minus 2 multiplied by 4 cubed all over 8 minus 4. This gives us 6c squared equals 1024 minus 128 all over 8 minus 4, right? This gives us 6c squared equals 896 over 4, which is 224. Hence, we have 6c squared equals 224, and c squared equals 224 over 6, which is 112 over 3. Solving for c, we get c equals square root of 112 over 3 plus or minus. Since this is a quadratic equation where we have the square on the left side, so we need to get the positive and the negative root. However, we discard the negative one since lengths are not negative and we have this interval 4 to 8, which clearly are a set of positive real numbers. So c equals the square root of 112 over 3. Rationalizing the denominator, we have 2 over 3 times square root of 3 over 3 is equal to square root of 336 over 3. But we can simplify this further into 4 square root of 21 over 3. But it doesn't matter since what we only need here is the value of c, which in some cases can be converted into decimals. But in our lesson, we should simplify it like this. 4 square root of 21 over 3 is the final answer. This is clearly between 4 and 8 since 4 square root of 21 over 3 is just 6.11. This is approximately 6.11. So this is our final answer. So our C is 4 square root of 21 over 3 inches. We are looking for the surface area, right? So we plug it back on the surface area. We have 6c squared as the surface area. Six c squared, which is 6 multiplied by 4 square root of 21 over 3 squared, which is 6. Let's just draw something here so that this won't be confusing. 6 multiplied by 4 squared is 16 times 21. 3 squared is 9. So we cancel the 9. Here we have 2. 21 divided by 3 is 7. So 3 times 3, 9. So the 9 below is non-existent anymore since we already canceled it. 2 times 16 times 7 is 32 times 7, which is 224. So the surface area that we need is 224 inches. Squared. So that is our final answer for this problem. Now, this is a problem from your third term exam. This can be solved in either mean value theorem for decimals or mean value theorem for integrals. However, for this time, we will be using the mean value theorem for integrals, which is much, much easier. Can you try solving this problem? So that ends our lesson for this school year here at STEM and Gene Review and Tutorial School. I would like to apologize for the delay in the uploading of the lesson since I have internet constraints. I hope you learned something from this and see you next school year if you will be at CERTS again. Good luck to your final exam. Thank you, everyone.